Okay, so now that I have my watershed boundary, I'm going to, I can use this information for all kinds of things. So I might want to take that boundary and take a look at the land use that's happening inside my watershed so that I have a sense of what type of activities are happening within the watershed that might be contaminating, that could be leading to a contamination problem. Let's say if we're measuring some pollutant in the stream. And I can also figure out the area of the watershed, which is really important when we're trying to understand how much water do we expect to arrive in the stream after any given rain event or snow melt event that might be happening in our area. So, in order to estimate the area of our watershed using our topographic map and our watershed boundary that we've just done here, what I can do is make a grid system over the over my map using, we already have an existing grid system here. So here I'm highlighting in these orange squares indicate 1 kilometer by 1 kilometer. So this would be 1 square kilometer, the area contained within this orange square right there. But those squares are a little bit too big for me to estimate my area inside of this little tributary's watershed because we're not filling up even one of these squares. So I'm going to create some smaller squares within those. So I think I'm going to draw some lines. And here I go. I'll do my best here. So I'm going to start out just about halfway point in that first square there. And it looks like that might be a little bit too high, so I'll center that. And then I'll just add some more of those lines to set up a grid system that covers, I want to completely cover my watershed area. Okay, so there we go. I've put my grid system in place, and I just did the minimal grid system necessary to cover my watershed. So you can see I'm still using the grid that's already existing in place, and I just what I find is easiest is to find the midpoint, and then from there find the midpoint again. So I've made it divided each of these into 16 4 by 4 squares within each kilometer squared there. Okay, and so now what I want to do is I want to count the number of grid cells that have at least half of the grid cell filled with my watershed. So that would mean I would count this one, but I wouldn't count this one because the amount of area in that grid cell taken up by my watershed is less than half of it. So I'm going to just be adding a shape to the grid cells that contain, that I want to count here. So I'll be adding one there. Let's see if I can make that a bit smaller. Okay. I'm just going to have to go with these really big stars because that's what my program here is letting me do. So I think I'm gonna actually count that one. It looks like that's a sort of a borderline, the one that I just filled in there. But keep in mind that the ones that I'm counting, even when they're just over half of the grid cell filled, they're going to be made up for by the ones that I don't count because they're just under half. So here's another one. Other one. Okay, there we go. So now all I have to do is go and count the stars, how many grid cells are filled up with my watershed. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so 14 grid cells are filled. Each of my grid cells are equal to 1/16 of a square kilometer. So I can calculate the total area of my watershed here by, let's see if I can write this out here. I would take the area of a cell, area of a grid cell. Oops. It's not writing very well. Is equal to 1 over 16 kilometers squared. So my area is 14 times 1 over 16 kilometers squared, which is 7/8 of a kilometer. Or about 0.88 kilometers squared. Okay, great. So now I can use this information to go move on and find out some other information about this system. So one of the things I can do once I found the boundaries of my watershed is I can go ahead and take a look at a satellite image, which is also provided by the USGS, where the same site where they provide these topographic maps. And so here I can see I remember my boundary was somewhere around here. Ooh, I got a really dark line. I'm not entirely sure why. So now I can look at, well, what's the land use within that watershed area? And so I can see, okay, there's my stream that I had seen. It's emptying into this much larger river down here. But it looks like all of the land within my watershed here is forest. So that means that I'll probably have a lot of infiltration happening in my watershed, not a lot of runoff, and I'm not going to be expecting to see a lot of the common contaminants associated with urban areas like oil and heavy metals and organic toxins like PCBs, and I'm not going to expect to see things associated with agricultural land either, like nutrients. But so I can expect that I have pretty good water quality there just from looking at my land use. But it doesn't stop there. What we can do once we've found the boundaries of our watershed, we can then go on and actually calculate how much water do we expect to get after a rain event. And we do that by, or we can do that. There are a number of methods for doing it, but one of the simplest that works reasonably well for small watersheds is to use a form of the rational method. So something that engineers do, in particular when they're changing land use in an area, and they want to see what are the implications for storm runoff. Here, what happens is they use this method where they're calculating runoff in Q, which is going to be equal to runoff coefficient, simply a number varying between 0 and 1, which indicates how much of the rain we expect to become runoff, times P, precipitation, or rain depth, and then the area of our watershed. And then you have to keep in mind what's not indicated on this equation, but that you always have to do when you're multiplying things of different units, is you'll have some unit conversion terms so that you make sure that you end up with a number in the right units that you're looking for. So we'll do an example here. So imagine we want to calculate the volume of runoff following 20 millimeters of rain. From our little watershed that we've just found the boundary of. So we know that the area of the watershed is 0.88 kilometers squared. our precipitation is 20 millimeters, and now our runoff coefficient, we just looked at the satellite image, so we'll take a look at what are the runoff coefficients indicated for forests. Well, they can vary depending on the soil type, but let's just take a common estimate would be 0.1, so about 10% of the rain that falls in a forested area we expect to see becoming runoff. Okay, and so to fill in this equation, we're going to have Q is equal to, our runoff coefficient is 0.1, there are no units associated with that, times the precipitation depth is 20 millimeters. You want to make sure that you keep your units when you're going through these equations, and you'll see why in just a minute. And then we're going to multiply that by the area, so that's 0.88 kilometers squared. But one thing to note here is I'm multiplying millimeters by kilometers squared, so what kind of units am I going to end up with? Generally what we want is we want our answer in meters cubed. Okay, that's a reasonable unit for a volume of water. So that means that I'm going to want to convert my millimeters into meters and my kilometers squared into meters squared. So I'm going to use these unit conversion terms. So really all that is I'm multiplying by 1, but 1 in a way that I'm setting some number of millimeters equal to some number of meters, and same with the kilometers squared. So here we know that 1 meter is equal to 1,000 millimeters. Oops, I sort of missed my line there. And then also, and the reason I put meters on top and millimeters on the bottom is because I'm actually trying to get rid of this millimeter term here, so I can actually cancel those out, because this is not a fraction there, so that's as if it's on the top of a fraction. And here we have millimeters at the bottom of our fraction, so they cancel each other out. And so we're going to end up with meters, which is what we want. And then here as well, we're starting with 88 kilometers squared, and so I'm going to put the equivalent kilometers squared at the bottom. So we know that 1 kilometer squared is equal to, let's see if I can fit all of this on the slide here. Actually, I think I might have gone off the slide. Alright, so it's going to be 1 with 6 zeros at the end of it. So it's 10 to the 6. 1, 2, 3, 4, 5, 6. Okay, and that's meters squared up at the top there. Alright, and that means I can again cancel out my kilometers squared here and kilometers squared there, and make it a little easier on myself, I'll cross out 3 of those zeros and 3 of those zeros at the top here. So now I'm simply multiplying these 3 numbers here and then times 1,000 there. So what we end up getting is 1,760 meters cubed is the volume of runoff that we get from that 20 millimeter rain event. So a really large volume can build up even from just a small depth of rain falling, because these watershed areas are so big, and it's funneling all of that rainfall, or all of that runoff that results from the rainfall, into our one particular stream channel there. So now what I've asked you to do for the first assignment is to take the time to look at another topographic map. This time it's for a reservoir. And this is also provided from USGS, United States Geological Survey, a U.S. government agency that provides environmental data, and we'll be relying on them a lot throughout this course. And so I want you to find the watershed area for this reservoir, and then you're also going to be using the rational method to determine runoff under 2 different land use scenarios here. So keep in mind that you're not only going to be wanting to highlight this reservoir, But you're also going to want to highlight streams that are draining into your reservoir. And so note this topographic map is a little bit more complicated than the one I had demoed on you. So for example, this solid line here is a tributary that's leading to our reservoir. And you can see that that sort of follows these upside down U-shape bends in the topographic line, so that's a good indication that you're looking at a stream there. So here's another stream as well. Keep in mind, though, that there are these other lines that are on this map that represent roads and human-built structures, and I think this might be a railway here. And then the other thing is that this reservoir has tributaries coming in, but it also has stream leaving it. So make sure that you notice the elevation. So again, look at these the numbers, the marked topographic lines to see is this stream that's connected to the reservoir an inlet, which is I'm going to want to use as part of my stream system for which I'm delineating a watershed, or is a stream an outlet for which that's going to be outside of my concern for finding the watershed that contributes specifically to the reservoir there. Okay, so good luck with that. Let me know if you have any questions as you're going through it, but hopefully this is going to be an activity that lets you hone your own watershed delineation skills.